So today we discuss galvanometer. What is the concept of galvanometer? Okay, that moving coil galvanometer. How galvanometer uses a voltmeter and ammeter. Okay, so what is the galvanometer? Now we know that in previous class, if there is a coil and that's the current direction I, so there is coil is create a magnetic field. Let's look like this. Suppose there is a magnetic field B, and now in that direction, current in that direction I. Okay, so current direction similar here, and that direction is I. From the magnetic field B. Here in galvanometer. Okay, so you see that there is a magnetic dipole. So if I place a bar magnet here, okay, bar magnet, that is the north pole, that is south pole, because the magnetic field released from north ending towards south, and that a magnetic moment, dipole moment mu in that direction. Okay, so here we place a magnetic field, external magnetic field as a north pole. Suppose that's the south pole, and that line is a curve because there is suppose a n number of turn here, the n number of turn, and the current direction. Okay, in the ending. Okay, that's the current direction, n number of turn, and the magnetic field. This curved line represents the crossing this coil. Here the magnetic field, external magnetic field, okay, cross this coil. Okay, and due to this, so here the current direction is in that direction. Okay, at that point is towards in that direction, and the magnetic field in that direction. It is B in that direction. So coil in that direction I cross B. So there is a force. This force is upward. That force is upward, and similar case I in that direction, B in that direction. So I cross B. So force is downward. The force is downward. So there is a rotation here. Suppose that rotation is in that direction. The rotation is tau. So now this bar magnet is slightly left direction, aligned to left. So it is bending here. Now that's the north here, there's the south here. To apply this concept in galvanometer, so here a indicator, suppose these are the indicator. Okay, indicator connect the bar magnet here, and the current carrying this coil, this green color coil, and now this indicator bent. This is the indicator, and there is a meter here. Okay, so with the help of this concept we design galvanometer. So here the torque, this is a rotation, this torque tau. Okay, so now we draw a phase diagram here. Phase diagram, there is a coil, so and that current direction, and behind that direction current. Okay, and there is a north pole, external magnetic field, that's the south pole, because the curved line, because the all magnetic field cross that coil. If I draw a state, there is an external magnetic field passing through that point, there is a loss. So here that I in that direction. Okay, and here is a bar magnet here, north and south, and the mu in that direction dipole moment. Now we attach a indicator here. These are the indicator and the North Pole obviously. Now if more current, so force is this direction, here the force is down direction, so we get a rotation here, there's a this indicator now slightly bent. This is the North Pole, the South Pole, this indicator slightly bent here. Now deflection suppose called phi, and there is a indicator here. Okay, so here is a torque tau, we know that is mu cos B, that's the B is the external magnetic field B, okay, and mu equal to NIA, okay, NIA is the number of turn current carrying coil, that's the cross section area A of that coil obviously, NIA, okay, and here you see that, and B, and that is a cross product, so that is a sine theta, so here the sine 90 degrees, so that is a 1, so tau equal to NIAB, and the sine 90 degree, obviously they are perpendicular, okay, so that is a sine 90 with a 1, because that's a magnetic field curve, otherwise there is a little bit change in magnetic field obviously, okay, that's not, if that line is not curved, so sine theta is not 90 degree. And you see the diagram very carefully, okay, and you see that is a bar magnet with turn, but I draw a coil with straight. Actually that coil also turn, you remember that, okay, this coil now with turn, is coil align this direction, okay, and not only if the bar magnet turn, then coil also be the turn. That's why the all magnetic field, that's why till here this is a curved path, and all magnetic field crossing that line. So if a magnetic field is that direction, now the mu in that direction, so now that angle also be that 90 degree. Otherwise, if I draw a straight line here, that straight here, now the coil turn here, and now that indicator attached to bar magnet here. Now the mu current direction in that direction I, but B mu in that direction, and that is a B in that direction. So this angle is not 90 degree, other than any value of 90 degree, okay, like less than 90 degree. So that's why this tau be changed. So that's why we design this is not a state, that is a some curved path. That's why the all magnetic field crossing that coil in perpendicularly. Okay, that's why mu and B, okay, mu and B are always in perpendicular. Clear the concept? If that indicator be turned, the coil also be turned. Now we attach that some sort of a spring here. Okay. Now attach this concept. Why spring attached here? Because back to that original position. Okay. Remember in mind. Okay. If that indicator also turn, means the coil also be the turn. Okay. Indicator coil are always in perpendicular. Clear? Jump to the next. At that case, always sine with a 90 degree when there is a curved line. So find tau equal to get NIAB. Okay, that's tau magnetic magnitude of torque. Okay, so here the current produced, there's a deflection here. This deflection as the indicator here. Okay, when I stop flowing current here. So now when I stop, so we attach a spring here. A spring to that coil indicator or the bar magnet. When the stop, current flowing stop, now this indicator, the spring push backward to the indicator for original neutral or that point. Okay, so here is a back point, this is called torque, and this torque is called restoring torque. Restoring indicator to the original position, that is 0 mark. Restoring torque. Okay, so here that restoring torque, the tau, that is some constant k depending on phi. K phi, there's a restoring torque, and torque produced by the magnetic field is torque produced by the magnetic field, by the B, these B magnetic field, and these also, okay, magnetic field, and that is magnetic moment, okay, magnetic moment, and these torque will be equal, okay. If more bending, so more phi means more restoring torque. That's why these two tau are with equal, and the K constant is called torsional constant. Okay, a torsional constant. Now these two tau will be equal. So tau magnetic field for B and tau for restoring. It is a B. That's for restoring these two. So B we get NIAB, that is equal to K phi. So deflection phi, that is equal to NIAB by K, and these tau obviously depending on the N is a constant, okay, number of turn, A area, this area, that's the constant, the magnetic field external, suppose there is a horseshoe magnet or any type of magnet here, that is a magnetic field also be the constant. So I here is a variable, so phi, that is N constant, A constant, cross section area, this magnetic field external, and the K torsional constant, I. These are the whole constants, so phi proportional to I. So more current here, more deflection. So more current get more deflection. So here, suppose that is called I, here is a phi. So it is a straight line. More current get more deflection. Okay, that's the concept of galvanometer. Now, this galvanometer uses as a voltmeter, sometimes it uses as a current meter. But there is a certain condition here. These galvanometer, these meter actually, this concept we cannot apply here, because the normal galvanometer cannot measure the current or voltage, because the first condition, galvanometer is a very sensitive device. These are the very sensitive device. First, these are the very sensitive device. A full scale deflection of like a very small microampere order. This full scale deflection, these are deflection in microampere order. And second case, galvanometer has a very large resistance. Okay, very large resistance. So they change the circuit current value. Okay, so that's why there is some change here. Okay, some external parts we added here, this galvanometer. Now that's after adding there's some parts, we galvanometer treats sometime treats sometime as a voltmeter, sometime as a current meter. Okay, now there's a galvanometer. Okay, so this is a galvanometer. Suppose a galvanometer look like this, a galvanometer, and there's a galvanometer resistance Rg. Okay, and we added some R here. Okay, and these are here, and these are added to that galvanometer. This R is added. Okay, and now there is a current direction I G, or suppose galvanometer current passing through that. Now we put a circuit load here. And one thing remember, if when I use galvanometer as a voltmeter connected in parallel. Voltmeter connected in parallel. So load that voltmeter connected here, there's the original circuit. That is actually original circuit. and these are the voltmeter. Okay, load resistance. Now here very important, if there is a circuitry current I, if that resistance is very large resistance. Okay, we choose that resistance is very large. So this current, if resistance I is inversely proportional to R, more resistance we get a less current. Okay, so maximum current passing through that load. So loss of the current is almost zero here. Okay, so now that's very important. The circuitry current be that same here, not change. That the main circuit current is not change huge. Okay, very small slightly change. Suppose like there is a milliampere order. Suppose a milliampere order, loss here is called nanoampere order. That's a very negligible change here. So that's why some huge resistance connect in series. Okay, so the ideal voltmeter, in case of ideal voltmeter has infinite resistance. Okay, ideal voltmeter have infinite resistance. Suppose now the Ig current here, suppose that the potential drop, suppose that's V. Apply the Ohm's law here, so you know that Ig, so Ig from V equal to IR, so V, and suppose these also the V here. Okay, same V IR, so R equal to RG plus these are the huge resistance, not load resistance here. That's we get a Ig current. Now here's another important concept here, voltage sensitivity. So voltage sensitivity, that's another important concept. Voltage sensitivity. From that equation we get phi equal to NAB by K times I. So phi equal to NAB by K times I. That's the whole constant here times I. So voltage sensitivity, when I find that is equal to divide by V here, both sides, and I by V, that is equal to 1 by R. So Q by V, that is equal to NAB by K times 1 by R. So here the voltage sensitivity is that if more resistance is less deflection. Okay, so here the less resistance get a more deflection. That's phi, more deflection here. Okay, that's the voltage sensitivity. Okay, that is depending on resistance. Okay, clear? That is depending on resistance here. That's the voltage sensitivity of voltmeter. Now, there's another important in case of a current meter. Okay, how to voltmeter uses the current meter. So, in case of current meter, you know that the ammeter. When a voltmeter treated as an ammeter, suppose there is a galvanometer, some very small resistance Rg. Suppose there is a current meter. Okay, that is a current meter. Now we choose a very small resistance added to current meter. Okay, suppose that is called Rs. Rs is a very small. Rs is a very small, and current meter always connected in series, and ammeter connected in series. When ammeter connected in series, the circuit current I, if that is a Ig here, and that is passing through that Rs, that is I minus Ig. If Rs is very small, so I minus Ig is very high. So if I minus Ig is very high, the main circuit current passes through that. Okay, so main circuit current is not vary here. Slightly change. Obviously, there is a milliampere, so that is a drop is a microampere. So that's why a very small current changes here. that is very low, very small, obvious. Okay, approximately 0. Okay, in case of ideal ammeter has zero resistance. Ideal ammeter has a zero resistance. So I apply KCL at that point derivation here. So okay, suppose that is IG and suppose KCL here, now apply KVL here. So IGRG, IGRG, and that is minus opposite direction. So put plus here, I minus IG times RS. So okay, so here is that RS, that is equal to IGRG by I minus IG. Okay, so here you see that that's the RS, and this resistance has another name. It's called shunt resistance. Shunt resistance, because the very very low. Very value is very low. It is shunt resistance, and here the effective resistance here is effective, that is equal to 1 by Rg plus 1 by shunt resistance. That's the effective resistance. The more resistance very small, more small, so more current. So main circuit current almost be the same, not deflected or changing abruptly. A very small change, that is an effect of the main circuit. Okay. So what is the current sensitivity? The current sensitivity of ammeter. So current sensitivity of ammeter now is very easy. That is equal to pi equal to NAB by K times I, and that is if here you see that is more current, so more deflection, so less current, and you see that is less deflection here. That's the sensitivity of actually the pi by I, we get NAB by K. That's the current sensitivity. Okay, that's the basic concept of galvanometer, how galvanometer used as a voltmeter or ammeter. Okay, so one question and note down, that's very important. Note that's change in case of current meter, where you use a very small resistance RS connected in a parallel, because the maximum current drawn from here, maximum main circuit current, and here the change is from voltmeter is a very large resistance connected here, because the current is very small, so maximum load current be the same. That's why voltmeter connected in parallel. Here that is ammeter connected in series. If large resistance connected here, the current value is very small. Maximum current passing through the mainly load or main circuit. Okay, clear? And that to change very large resistance here added in galvanometer connected in series, and very small resistance connected in parallel with galvanometer. That's to change. Okay, why this change is needed? Discussing here. Because the normal galvanometer cannot measure the current voltage, because the for galvanometer is very sensitive. Why not? Why normal galvanometer not use voltmeter or ammeter? That's very important question in board exam. The answer is 2 point. Galvanometer is very sensitive. Is very sensitive. Okay, very sensitive. A full scale deflection almost in very small, and full scale deflection. Full scale deflection means here to there. That's a full scale deflection. Here to that, that's the full scale deflection. Actually, the meter over here. The full scale deflection is a very small, almost microampere order in current meter. Number two point is galvanometer has a very large resistance. Galvanometer has very large resistance. So they change the circuit current. So they change circuit current, main circuit current. So very small, almost zero resistance connected in parallel. Because of if a small value of connected in parallel, some resistance connected in parallel, so maximum circuit current passing through that resistance. This look like this. Maximum current passing through that resistance. So that's why main circuit current is almost same, not very huge. Okay, almost negligible change here. Okay, that's why a shunt resistance, a very small value of resistance connected in parallel. Okay. Clear? There's a basic concept of galvanometer, voltmeter, and ammeter. How galvanometer uses as a change to voltmeter, how galvanometer change to ammeter. Okay, and the concept of galvanometer. Okay, these two are very important concept, and this concept came from previous class. That previous class is very important. And if you doesn't know what is the magnetic dipole moment, so there is a typical. It will be difficult to understand what is the galvanometer. Okay, so my suggestion is that you study the previous lecture or cover the previous lecture, then you see that lecture. Okay, so we complete that our class moving charge and magnetism, and next class we solve some important question of board exam or JEE NEET exam. So if you have any doubt, you ask in comment section. I will try to give the answer. Next class we meet a new concept, new topic, or new numerical, obviously. Thank you.